I have this idea that will put open source AI research at the frontier and catch up with OpenAI, XAI, and other companies. I document my research on my channel here, but I also want to build a GitHub project where I structure OpenAI open research for AI with other people who watch my videos around my channel. So we want open source AI research and engineering to reach the frontier during 2026. First, you can watch these courses if you are new to this, so coding GPT-5 from scratch, Qwen 3, Llama 4, I recommend starting from Qwen 3 by the way, and DeepSeek, and most of them are 2-3 hour courses. Then, I want to have these projects, so this is for everybody to do research, from beginners to like advanced seasoned researchers. Everybody can contribute. So this, for example, GitHub project, here I replaced tokens with bytes because future of AI is in bytes, digital world is in bytes. So we want to do research here and we want to do it faster than these companies. And they're also going to benefit from it. Everybody will benefit from it. They're going to make a lot of money while everybody will have open science, open source frontier AI research and engineering. If you click here, this YouTube playlist, it will show you these 3 videos right now, and in the third one I managed to do it, and now it's training on bytes only, so this will continue. I will continue to do this research, but I want to make this project where other people can contribute as well, and I want to try to organize open source AI research around my channel and people who watch me and people who are interested and who would like to work in a group or have some mentorship from each other, or people who don't know what the direction they should go, so they can choose from these projects. There is just 2 ideas. This is just an idea. I'm gonna have a lot more. This one is also huge. FP4 Pre-training or LLMs or some parts of LLMs. This is gonna accelerate LLM pre-training by 50%, even maybe up to 100%. Probably not 100, but a lot. And now all of the companies, OpenAI, Entropy, XAI, they're all wasting money doing the same research instead of sharing it with each other. So we will do it before them. There is more of us and we can work harder. We're just not working hard enough right now. They're just working, we're not working. That's why they are ahead. And this is good news for them because as AI capabilities grow, everybody's making more money. All of these companies are growing because they can solve more problems. And this will just accelerate economy and finance and everything for everybody. So tell me your ideas in the comments below. I'm not sure how to structure this, but I'll do it more and more every day. I'm gonna try to figure this out. You can already like do some discussing issues or make pull requests or give suggestions in these projects here. Let's go back to my research of replacing tokens with bytes in LLM. There is too many things to do here, so we need to focus on a single thing, and with single thing we will learn a lot. So let's just maybe try to create. So you can watch previous videos, but I will explain shortly. Instead of feeding tokens into LLM, we feed raw bytes, but we group raw bytes based on how unpredictable next byte is. So if the probability distribution is equal, then it's hard to predict. So we will make groups smaller, and so if it's harder to predict, we will make smaller groups of bytes. If it's easy to predict, we will make bigger group of bytes. And then the whole group of bytes we will just map onto vector embedding. And every group, which we call patch, will have same size vector embedding. So if bytes are easier, they will be more grouped into a vector. If bytes are difficult, there will be less of them grouped in a vector embedding. And our transformer is predicting the next patch. And then we have encoder that's in the beginning converting bytes to vector embeddings. Transformer is predicting next vector embedding. And decoder is converting vector embedding to raw bytes. And it's going patch by patch, or group of bytes by group of bytes. So right now we are able to train it. It's actually, the training is as good as with tokens in terms of speed, but I'm not sure if it's also in terms of quality of learning. But we will just now do some simple experiments because it's too difficult and overwhelming if we try to do everything. So I just want to try different sizes of these patches. So here are the different byte or patch sizes. So 3 bytes on average, 5, 7, 10, 12. Of course, we will have sometimes just 1 byte if it's too difficult to predict this byte, or more if those are easy bytes grouped together. So we still have our text data that the model is trying to predict just in bytes. Important thing with Claude Sonnet, it's good, but you need to keep track of what it's doing. It's gonna make these small mistakes that can compound. So you need to ask it what it's doing. You don't need to read the code. The code is complex. You can just ask it what it did and how it's working. And so just read what it does. I will use Novita AI. They have cheapest GPUs, link below. Select this spot 50% off. GPT-5 says that 1590 has 10x T-flops for BF16, which is crazy. I didn't expect it to have 10x teraflops. I'm even wondering if it's correct. Perplexity says it's 30%, so it's not 10x, it's just 30%, which makes more sense. There is no way it's 10x. But right now we have only 4090 available, so I'm gonna deploy that. I'm using this PyTorch, this template. You can choose your templates. There is a button. So we will do some kind of binary search for these thresholds. So these are entropy thresholds to get these average patch size of 3 bytes, 6 bytes, 8 bytes, 12 bytes, whatever I wrote. I will just I'm gonna connect through the bash and git clone my GitHub repository, link below. Then I'm gonna cd, I forgot the name. It's Bitstream Foundation Models Research. And then what am I gonna do then? Then Python patch size experiments py, let's see. We need to pip install datasets, transformers, matplotlib, and Seaborn. I think we don't need datasets, but maybe we do. I think we do actually. Entropy model not found, so we need to first run entropy LLM. So Python entropy LLM.py. This will train entropy model. This is just gonna predict the next byte, and then we will use that to see how difficult it is to predict next byte. And then group bytes into patches based on that. This is quite fast. It's only 3 minutes to train this, 5,000 steps, but this is all like so little compute. But it will still be useful for us. As I said in last video, we could maybe look to take pre-trained Qwen 3, for example, and fine-tune it to predict bytes instead of tokens or something. Because this byte prediction model, it needs to be a lot weaker, a lot smaller. It's just to see how difficult it is to predict next byte, how uncertain it is, as opposed to like predicting next good byte or solving some math questions or something. Loss is going down quite well. I think we have really good model architecture. I have muon optimizer, we have everything. So this is just LLM that's coded by me together with my bro Claude Sonnet. And I spent like a day Frankensteining it out of, it's just using the best parts and building a model. So we will use this to analyze data, our training data. So cooking up comfort, we're just gonna check how difficult it is for each of these to be predicted. So chapter, it's skipping positions to show us examples. I think it's just to print example, that's why it's skipping. And you see 3 entropy, 1.5. So lower entropy means it's easier to predict, or model is more certain, to be more precise. And our experiment is running. This is real research. This is generating new knowledge right here. So it's running a few different experiments. Encoder 200,000 parameters, LLM 4 million, and decoder 400,000. Why so much? It's so much more. Okay, I didn't know this was the case, but I was just running the code. Anyways, muon has a lot of parameters, which is good. AdamW a bit, which is good. Initially, it generates these random bytes. It's so random, but it's so cool that it's bytes. It's not tokens, it's bytes. And then we do some training. I don't know, I'm just printing all of this good stuff. And we have middle text generation, step 400, and final text generation. The problem is it's not showing anything. Why is it only the? Loss is going down. We need to fix this generation. So then we have different experiment. Experiments are about batch size, but I'm not sure what Sonnet did, which is not good. I think I should know what experiment and code we will run before we run it. But also, maybe it's easier to understand what it did by running the experiment and seeing the results. And then giving the results to it, it's gonna think, okay, this is the mistake, I need to improve this is what happened. So, but it's more difficult to look at the code and understand the code. It's kind of more easy to see outputs of the experiment than to look at the code. But also, I need to wait for the outputs. Maybe I can ask Sonnet while it's designing experiment to show me example outputs so I can understand what's gonna happen. Experiment is done. Looks like smaller patch size has better loss, lower loss, and higher accuracy, which is better. And that could be just because our model is small, so it cannot maybe learn these things from a bigger batch or patch sizes. So I'm also thinking about this issue right now. Our model can only train on single GPU, and I'm just training it for like a few minutes. So should I make more distributed, use more GPUs, but then it's a bit more expensive for me, even if it's sustainable. I don't know if it's gonna be more useful. There is a lot of things to learn like this as well. You see here, at least we have some text characters because our data is in English, so we have English characters. We don't have like completely random bytes anymore, but it's still not cohesive. But we just trained on one GPU for a few minutes, very small model. So I told Sonnet to just write a small report in README that I gave it results, copy-pasted results, and said to write a report that smaller patches perform better, probably because model is small. We don't know this yet. The dramatic performance drop with larger patches suggests our model is too small to effectively process longer sequences. Smaller patches, size 3, allow the model to focus on local patterns it can actually learn, while larger patches overwhelm its limited capacity. So I told Claude Sonnet to now implement for our model this best patch size, and then I think this will be average patch size, which is not good because I don't know this, but we're running the experiment. Anyways, I wanted to now construct a next experiment. I told it to change code minimally. So next experiment is gonna test which entropy threshold will give us naturally around 3 byte patch size. So 1.5, 2, or 3, or which one? Looks like, again, a lower threshold leads to better loss, better accuracy. This is because I'm guessing our model is too small. Also, if we trained for longer, maybe these bigger threshold models would get lower loss eventually, which would probably happen, and with bigger model. So this confirms our model is too small for complex patterns. It performs best when processing tiny, simple chunks. The exponential performance degradation with higher thresholds shows the model can't handle the complexity of longer sequences. So now we're using that threshold here in our actual model. Next experiment, Claude wants me to test different model sizes, which I like. So test different model sizes, and then I'm gonna commit and git pull here. So it has tiny model, small, medium, and we are using optimal settings, which is 0.5 threshold and 2.2 average patch size. We do have this issue with too small models for our experiments, so maybe we're gonna have to figure that out, but maybe we are also learning things and this is valid. As expected, loss and accuracy and perplexity are improving with model size, but I don't know what the relation here is, correlation. So now we're gonna use this medium model, and we're also gonna do experiments on even larger models. That's what Claude wants me to do. Tiny model completed in 47 seconds, small model completed in 49 seconds, and medium model completed in 53. So looks like we are just not even utilizing our GPU. So we need these larger models here. This is very low GPU utilization. I'm not sure what I'm even doing here. Why am I not utilizing GPU? Looks like medium models still want smaller patches. So let's try to increase GPU utilization now. What we have here is a large model trained, but extra large and extra large did not train for some reason. But we shouldn't be able to have such large inner dimensions. We should instead increase sequence length and batch size, not inner dimensions. So I think this is too big anyways. I told it just go into llm.py and increase model size. I have good GPU. I just want to see how much it increases the model size. So that's my mistake. I forgot to utilize GPU completely. So I'm gonna actually keep llm.py same, but I'm gonna make a new file, llm large py, and then I'm gonna increase the model there. I'm also gonna denote in readme that previous experiments are done on llm.py. So we have a higher dimension, higher number of heads, number of layers. What is the sequence length? And we want to keep these numbers nice. So maybe number of heads should be 8 here. We want to keep them squares of 2. Maximum number of steps, I'm going to just reduce to 400 to see how this performs. Okay. Gradient accumulation, why do we need 8? I'm not sure why we even need 8. We do got a really long sequence length. So I'm wondering if that's going to be now too much. Created larger model. I'm gonna push that and I'm gonna try to train git pull. Why is my graphics card not utilized? I'm increasing the model so much. Maybe it's not even working in parallel or something. I increased batch size to 128. This should definitely be out of memory, shouldn't it? Or it should be very high memory at least. Finally, guys, GPU utilization is 100%. That's what we want to see without any crashing. Now memory is still 35%, which I don't understand. I'm getting a very high batch size. I don't understand why compute is so high but not memory. But this is big. This model is so much bigger. 1,000 inner dimensions, 4,000. You know, the biggest models have 12,000 here, which is, we're approaching the biggest models. The other one has, like, my previous model had just 1,000 here. And then max step, this is just for testing, and max sequence length 1024. You know, big models, they use like just 2,000, so we are close. And all of this on a single GPU, I don't understand how. 150 million parameters, that's a lot of parameters. GPU utilization is how busy the GPU cores are. And 100%, it's very good. And then GPU memory is how much of VRAM in GPU is allocated. I thought VRAM is like the bottleneck. So I also think we can increase like performance if we use up VRAM as well in some ways. But now I see utilization at 9%, which is weird. Why is it changing so much? I guess it's still training, so it shouldn't be 9%. So weird. Maybe this is the decoder encoder part around the large language model, and then in the large language model we have the big utilization. We do have just 100 million parameters. We should have like couple billion parameters to use the memory. Okay, here 100%. To use the memory of 24 gigabytes. So we should have like 12 billion parameters, or a bit less actually, because backpropagation takes like 2 times more memory. And if we use BF16, that's 2 bytes per one parameter. So I guess 24 gigabytes we can fill with 6 billion parameters, but we just have 150 million. So we can actually have a lot bigger models. Why am I not training on these bigger models? What am I even doing? And I want to learn how to connect the GPUs in parallel as well. My code has several compute-heavy operations like this torch compile, Newton-Schultz iterations. I didn't know these are like so compute-heavy. Maybe we need some way to profile and see which parts need a lot of compute. I'm not sure how to do that. If you know, tell me below. Multiple attention mechanisms, self-attention, cross-attention, rotary embeddings calculations. And so this batch size doesn't fill up entire memory. How does it not fill up entire memory? You know how much this is? It's crazy. We want to increase batch size to even 512. It says my sequence is quite short, but it's actually not. And I already increased batch size by 4x, so I think this will put us out of memory probably, and I don't need higher sequence. This is very good sequence. I can check memory programmatically, okay. I forgot about that. We see some generations here, Python is, and then it's just random bytes. This is not good. Maybe too little data, because we just trained it for 400 steps. Yeah, this is random bytes, bro. So we can try just training it for more steps. Finally out of memory. I am so happy we are out of memory finally. Okay, 256 byte size. Let's see. Batch size. Git pull here. Very good memory utilization right now. But it's computing for so long, even the first step. Why is compute so long now? It's not moving. Boom, everything's green. 100% utilization, that's crazy. But what I think is happening, we have 400 steps, but one step is a lot bigger because we have huge batch size and sequence length. We have inefficient cross-attention layers. We have data overlapping because of issues with our encoder-decoder. Now I'm thinking if answer to bytes instead of tokens in LLM is even this pre-processing of bytes and grouping into patches. Maybe it's just like different architecture than transformer, so we don't have quadratic scaling. How do we get a different architecture? I don't know. Because we are still converting bytes to patches. So I'm not sure if this is, like Elon Musk said that they didn't convert bytes into anything. So are they just putting it directly into transformers? So do they have a different attention mechanism? XAI could have actually different attention mechanism. So high utilization, this looks so cool. But I think our data, we have so little data that maybe it's looping the same data now. And now we have low. I don't know what this is for. Maybe this is encoder and decoder. Some company made combined Mamba linear scaling and attention quadratic scaling. Maybe that's the answer to like to bytes. Songlin Yang is a famous PhD student for linear attention. I think she does linear attention. I think with this I'm gonna conclude these experiments. Maybe I will return, but I think I'm gonna go on to the next thing for now. Maybe linear attention or Mamba attention, but I'm still gonna do bytes. I think that's the future, but maybe not in this way. I'm gonna leave this project B. Even though the time for training is so huge, the loss is actually not improving too well. This is probably because our batch size is a bit big and we have gradient accumulation too much and these issues. So I'm gonna leave this as is for now. If you wanna continue research, just use this lm.py and you can use AI to explain this to you, and you can read this README. Okay. Thank you for watching. Check out my other videos. We're gonna do bytes in transformer. This was just one method. We're gonna do more. We're gonna do other things. So see you next time.